Hello everyone, and welcome to the Rotational Inertia Pre-Practicum. So I wanted to, at this point, kind of give you some experience with rotational inertias in the lab setting, as much as we can. It's going to mean a setup very similar to ones that we've used in the past, but basically you have two objects. You've got a disk, solid disk, and an annular cylinder. And we'll talk more about an annular cylinder, which is really a thick hoop, all right, in a moment. And I want you to figure out the mass of the disk and then also the mass of the annular cylinder from a rotational kind of standpoint. Not just putting it on a scale, all right, or doing something else like that, but using rotation. Okay? So the way this is going to work is you are going to, for each object, because you're going to do the disk and then the annular cylinder, you're going to open up a file, which is here, right, called angular acceleration, which is basically just a big angular velocity time graph. And hopefully by now you know what you should look at on an angular velocity versus time graph to get the meaning that you need. Right? Then you are going to attach to the rotary motion sensor the disk, except you are not allowed to attach the disk through the center of mass. That's too simple. I want you to attach it through a different place so that the axis of rotation is a parallel axis, hint, hint, right? Not through the center of mass. And the same thing when it comes time for the annular cylinder. Okay? You can't really put that through the center of mass because there's too big of a hole there, but you can put it at other points, as you'll see on the device. Okay? So it can't be through the center of mass. That's too easy. Then you're going to set up the lab equipment the same way we've been setting it up the whole time. Super pulley should be at an angle. String comes off of the largest pulley so that it comes off tangent. You got to tilt the smart pulley a little bit, right? The largest pulley is 0.024 meters, which you're going to use. And you're going to place a 10 gram, 0.010 kilogram mass onto the mass hanger. So your hanging mass is going to be 0.015 kilograms. Okay? Then you need to run a lab and do the physics so that you can calculate what the experimental mass is of your disk, and then do the same lab over again, but with the annular cylinder. You have enough physics and enough knowledge of how these things work to be able to do this, okay? Once you get an answer for your disk, bring it over. We'll check it on the electronic balance and see how close you are. Right? Same thing for the annular cylinder then when you're done. Now, you already know everything you need to know about the rotational inertia of a disk, but an annular cylinder is not one we've discussed before. So we're going to have to do a little proof as part of this pre-practicum, and that is that we're going to need to find the rotational inertia of an annular cylinder of mass capital M, inner radius R1, outer radius R2, and uniform density about an axis through its center. So if that's the axis, right, that's the axis through its center of mass, essentially. Now you might be saying, well, how can I do that, right? Well, you can't experimentally with our device, right? There'd be no way to screw that in that way. But let's say we had a rolling annular cylinder. Then it would be rolling around that point, yes? So that's still an important point to determine the rotational inertia around, okay? R1 is the inner radius, R2 is the outer radius. Okay? All right. So, as we've done many, many times, in order to figure out the rotational inertia of this annular cylinder, we're going to break it up into little mass elements. Now, my little mass elements are going to be hoops which have a radius, inner radius of, a mass of dm, a thickness of dr, and a radius, an inner radius, of little r. You okay with this? And we'll take these little hoop elements and ones that are right along the inside, and we'll sum them up to the ones that are right along the outside. So again, each little mass increment here. Now, kind of like when we did disks proof earlier, these are technically infinitesimal, so my picture is a little bit disingenuous, right? It looks like there's only like 2 or 3 of these in the whole annular cylinder. remember, dr and dm are infinitesimals. So these are vanishingly small, thin, that's why I'm calling them hoops, right? So I just can't show that very well in a picture, okay? So be aware, we're doing calculus here. So as we know, the rotational inertia of a continuous object is the integral of r squared dm. But, right, we've got a little problem here, right? Our problem being that r and dm are two different variables. So we're going to have to do a change of variable. And as we did with a disk, we're going to use two-dimensional density. It is, after all, a uniform density annular cylinder. So that means that the total mass divided by the total area is equal to the mass of our little increment all over the area of our little increment, right? Our little hoop here. Okay, so these things have to be the same because, you know, the uniform density of any piece has got to be the same as the uniform density of the whole. That means, right, we're going to solve for dm, but what is dA? What is the area of this little mass increment here? This little hoop. Okay, well, that area we could find by taking the area of the outside of it and subtracting off the area of the inside of it. Right? And what we would leave would be the area in between. You with me? So that's going to look like this. Okay, the area of the outer one. Now notice the outer ring here is a radius of r plus dr. Right? That's the radius of the outer part of it. That's squared, so it's pi r squared, remember. We did that in a lab back at the beginning of last year. And this then is, the inner one is just pi r squared. Okay, so this is the area of that little increment. Again, if you're saying this looks familiar, we did a similar thing for disks. All right, now we square. Notice that the pi r squared here and the minus pi r squared there cancel. And then you have to remember here that this is an infinitesimal. So this is a vanishingly small thing, and if you square it, you still get a vanishingly small thing. In other words, that's essentially 0. I know that's weird, but that's the calculus part of it. So the total amount of area of this ring is 2 pi r dr. It's the circumference times the thickness, if you will. Okay? So that's going to plug in there. So solve for dm, that gives us m over a times 2 pi r dr. We plug that into the integral, and we have changed the variable. Now, before I show you that, let's talk about limits of integration. All right, we want to pick up all the little mass increments in here, all these little hoops. So the smallest hoop will have a radius of r1. The largest hoop would have a radius of r2. So we're going to integrate from r1 to r2. And this is r squared times, and this is our dm, right? M over a, 2 pi r times dr. Well, m, a, and 2 pi are all constants and can come outside of the integral. R squared times r is r cubed. So we're left with the integral, 2 pi m over a times the integral of r cubed dr from r1 to r2. Well, the integral of r cubed dr is simply add 1 to the exponent, divide by the new exponent. So that's 1/4 r to the 4th power. We've got to evaluate that at the upper limit, and then subtract off evaluating it at the lower limit. And notice I moved the 1/4 outside, and 2 times 1/4 is 1/2. See where that 2 popped up, right? 2 times 1/4 is 1/2. So this is r squared, r2 to the 4th minus r1 to the 4th. Okay, and then we're picking up just the annular cylinder. Okay. Now here comes the fun part. We need A for the annular cylinder. We need the area for the annular cylinder so that we can substitute it in and do some simplification. For a disk, that was rather simple, right? The disk is just pi r2 squared. Right? But this isn't a disk. So how we're going to figure out the area is that it is the area of the outside circle minus the area of the inside circle will tell us the area in between, right? Similar to what we did for our little mass increment. So it's pi r squared, or r2 squared, minus pi r1 squared. If I factor out a pi, for reasons you will see in a moment, I can then plug that in for the total area and get that. Notice that the pi's will cancel. And now let's have a little fun with factoring. I want to factor this to make it look more like this. So my supposition here, and I think I can convince you, that r2 to the fourth minus r1 to the fourth can be written as, right, so those cancel, so that's what we're left with. I can rewrite this as r2 squared plus r1 squared times the quantity r2 squared minus r1 squared. Do you see why? It's a lot like the difference of squares, but it's actually the difference of, I don't know what you'd call that, things raised to the fourth power. Right, so if you look at the inner terms, right, your r1 squared, r2 squared from here, and then you're going to have a negative r1 squared times r2 squared from there, and those are going to cancel. Right, so you'll just get the r2 to the fourth and the r1 to the fourth kind of thing, okay? Now, why did I choose to factor it that way? Well, because, notice, there's an r2 squared minus r1 squared on the bottom, and there's an r2 squared minus r1 squared on the top, so we cancel those two out, and there's our answer. This is the rotational inertia of an annular cylinder about a central axis. Theoretically, you're actually supposed to know how to do that on an AP test. Very similar to a disk, but you got to deal with the hole. Right. Now, I want you to notice something here, okay? I want you to notice that the rotational inertia of a solid disk is 1/2 mr squared. In this case, that would be r2, right? So notice that this rotational inertia is larger. You're adding the r1 squared in here, right? It's larger. Do you see why the rotational inertia of an annular cylinder would be more than the rotational inertia of a solid disk of the same mass and total radius? And that's key, right? These have to have the same mass and the same radius. That would be tricky, but it could be done. Do you see why? Isn't the mass concentrated further away from the axis of rotation for the annular cylinder? Yeah? And when mass is further away, there's more rotational inertia. Right? So it makes sense that we got an answer which would be related to a disk, but bigger than a disk. The other thing I want you to notice here, just because it's kind of fun, what happens to this as R1 approaches R2? In other words, as the hole gets bigger and bigger. Right? Well, if the hole starts getting really big, so that R1 and R2 are almost basically the same thing, then this would be 2r2 squared, and 1/2 and 2 is a 1, and you get a rotational inertia of mr2 squared, which is the rotational inertia of a hoop around the central axis. See that? Which I hope makes sense, because if R2 and R1 essentially are the same, then you've made a very thin hoop. I know, all these fun things, and a lot of them you can kind of get a handle on, or you can get an idea of what it's supposed to be, right? Even if you don't have the equations in front of you, you can compare one to the other. They like to ask those kinds of questions on AP tests, especially AP1, but even sometimes in AP2, where you can compare the rotational inertia of objects by kind of looking at how they're formed and their mass concentration. So, given this, the rotational inertia of your annular cylinder about the central axis, and information you can find from the experiment and other things that we know, you can figure out the mass of your annular cylinder, which then you can bring over to the electronic balance and mass and see if you got everything right. Enjoy this little rotational inertia practicum.